Okay, now we want to use ARIO to determine which of the indicated hydrogens is most acidic, and this is very similar to Skill Builder 3.9 in your textbook. So I have a green hydrogen and a red hydrogen on each of these four molecules. So the first thing I want to do again is remember the acronym. Do we have different atoms that these hydrogens are attached to? And indeed we do. We have a nitrogen. So I'm going to draw the molecule with a nitrogen hydrogen removed, or I could draw the molecule with the oxygen hydrogen removed. And remember the question, the first question, determine which hydrogen is more acidic, is also can be rephrased as which of these anions is more stable. It's going to give you the same answer. And in this case, I think you'll see that we have an N- versus an O-. They are different atoms, and they are in the same period. They're in the same row. So, same row, that means more electronegative atom will be more stable. And so that's going to be the O-. And so in this case, it's the green hydrogen that's most acidic, using the A form of ARIO. The oxygen versus the N, O- is more stable than N-. Let's look at the next example. We have an OH and an OH, and so in this case there are no differences in atom, but I think if I draw the two possible anions, you will agree that there is resonance possibilities for one of these oxygens and not the other. This one has resonance. I'm hoping that's becoming second nature to you to observe. And this one has no resonance. So the red hydrogen is going to be the most acidic hydrogen here because its anion, the anion that's formed when that hydrogen is lost, has resonance stability, whereas there is no resonance stability for the loss of the green hydrogen. Let's look at the next molecule here. Again, we have two possibilities. We have an O-, that's on the ring, and we have an O- that's sort of on the side chain of the ring. And we're going to try to figure out which of those is more stable. Now these are both oxygens. They both have negative charges, so atom doesn't help us. Does resonance help us? Well, this O- has no resonance. And that's because this is a fully saturated carbon that is attached to. It cannot accept any more hydrogens. There is no pi bonds, no adjacent lone pairs. There's nothing we can do with this charge. However, this O- does have resonance. You should recognize it as an allylic lone pair. Now we can draw resonance. I'll try to use a different color here. Following these two arrows, which gets us to this resonance structure here. And we can draw several more resonance structures. So there's two more resonance structures that are possible in this case. And so the red hydrogen is going to be more acidic because its conjugate base is stabilized by resonance, whereas the conjugate base of the green hydrogen is not stabilized by resonance. And lastly, let's look at this bottom molecule. If I lose the red hydrogen, I get an anion on the ring. And if I lose the green hydrogen, I get an anion on this sulfonate group down in the bottom. So you might say, well, hey, that has resonance. But remember that this lone pair resides in an sp2 hybrid orbital. It does not reside in a p orbital, which is required for resonance. So this lone pair is not resonance stabilized. And of course, you'll recognize that this hydrogen is a vinylic hydrogen. It is a hydrogen attached to a double bond. Those are not typically acidic, and that's because they are not resonance stabilized. Whereas down here, we've got some lone pairs, and we can show some resonance happening. I'm not going to show all three structures, but I'll show you the second one. We can put the negative charge on the left oxygen, and we can also put it on the right oxygen. I'll leave that up to you to show me. So this green hydrogen is the most acidic hydrogen in this bottom molecule because it's attached to not only an oxygen, so it wins with A. I should have started with A, not resonance. Not only is it an O minus versus a C minus, but that O minus has some resonance too. So we have both A and R in this case helping us out.